All right, Physics 11. We're going to keep going with our latest unit. So we just finished a lesson on talking about work, right, and how we calculate, work done on an object in motion. And that formula involved taking the force parallel to the motion and then multiplying it by the displacement. Okay. What we're going to be looking at today is what happens when force is actually on an angle, right, and how would that potentially affect our calculation with work, and then therefore how does that affect other calculations, such as like calculating force of friction if something is on an angled ramp. Okay, so that's essentially what we're going to be looking at today. So we will get into that now. All right, so like I said, we'll be looking at calculating forces that are on an angle at this point to help us with other calculations done with work, right? So as mentioned, work is not always done perfectly parallel to the ground, right? We're not always applying a force that's exactly parallel to the motion that's perfectly horizontal, okay? And sometimes we do need to factor in an angle, okay? And in that sense, okay, what we do is we just multiply our typical work formula, force times our displacement, and we multiply it by cos theta. Okay, the reason we're multiplying it by cos theta is just kind of think right angle trig again, where if you're applying the force at a different angle, and theta is that angle that it's making with the ground, okay, that, using your cosine ratio will give you the adjacent side length, and again, you'll see it better when I draw the diagram, but it gives you that what the force would be parallel to the ground if your force was being applied at an angle. Okay, so application of this formula occurs when the motion of the object is perfectly horizontal or perfectly vertical. Okay, so what this means is that this formula can be used to calculate work done on an object. The object still needs to be traveling in a perfectly horizontal or a perfectly vertical motion in order to use this simple formula. Okay, if your object is actually occurring on an angle, okay, so that means, like, let's say we're talking about something moving up and down a ramp, right, or up or down a hill, right, that motion is on an angle. All of a sudden we've got to bring in a whole bunch of other things. We have to think about normal force coming into play. We have to think about possible friction of the ramp or the hill or whatever the case may be. Okay, so in those situations, which again we'll be looking at in this lesson as well, we need to look at all of the different forces acting upon that object. We need to incorporate that angle, and we would need to, calculate forces of friction. We'd have to use our trig ratios to be able to get the relevant forces. Okay, so again, you'll see these examples today about what I'm talking about, right? So there's a difference between when your motion of the object is perfectly horizontal, right, flat, or vertical, up or down, versus a little bit more work that needs to be done when an object is actually on an angle, right, like a ramp or a hill. Okay, and then don't forget that normal force that's acting on an object acts perpendicularly to the direction of the applied force. Okay, so normal force is not just straight up, it's perpendicular to the direction of the applied force. All right, so that if the applied force is being done at an angle, right, if the object's at an angle, it could mean that your normal force is also kind of angled as well. And again, you'll see that when we get to these questions. Okay, now if your motion is just straight up and down, okay, then using that work formula here, right, of force times displacement times cos theta, if you're going straight up, that angle is considered 0 degrees, and if you're going straight down, that angle is considered 180 degrees, okay? And using cosine of those values, right, cos of 0 is actually just a positive 1, right, meaning that the work done will be positive going in the upwards direction, whereas cos of 180 degrees is equal to negative 1, so it would be the same value but done in the negative direction, okay? So this is the diagram I was talking about in terms of thinking about where normal force is and an object that's potentially on a ramp, okay, so on an incline. So what will happen here is if your object's here on the ramp, right, and the ramp has an angle with the horizontal given here, your force of gravity always pulls straight down, right? So notice how it's not going that way. Your force of gravity pulls directly straight down, and because your object is on a ramp, your normal force isn't just opposite your force of gravity. Your normal force is perpendicular to the ramp here, okay? So perpendicular to the object's motion. So the object is moving down the ramp this way, right? And we'll call this force parallel because this is the force that's parallel to the object's motion, right? It's going in the exact same way, right? If there was friction here, force of friction would be pulling this way, right? Back up the ramp. Again, force of gravity pulls straight down. And your force parallel, can actually be found using this kind of little triangle here, right? So force of gravity pulls straight down. Then what you can do is create this line here that would be perpendicular, right, to that normal force here, right? So normal force this way, and this would be equal but opposite to that normal force value, okay? And then this line here, right, this would be a parallel line to this one here. So calculating this value gives you the force parallel here. And what happens is when you draw that straight down force of gravity and then you draw these other lines which make this nice little right triangle, it creates a similar triangle in the sense that, you know, this right angle becomes this right angle, and this angle, the angle of the incline of the ramp, is this angle up here, okay? So force of gravity can typically be found using just your mass times your 9.81 meters per second squared. So you have this value, and if you notice, what you've drawn here is a right triangle. So what you've got with this force of gravity is a hypotenuse. And if you have this angle, that's enough to find this length and this length, right? So using this angle, and this is your hypotenuse, this here, the force parallel value, would be the opposite of that angle, right? Opposite over hypotenuse. So you'd use the sine ratio to solve, and this force parallel will be equal to the force of gravity multiplied by sine theta. This value here, right, which would contribute to the normal force in this case, right? This would be the adjacent side of that right triangle, and again, adjacent with hypotenuse, you'd use the cos ratio, cos of theta multiplied by f of g, and that would give you that value there. Okay, now again, we'll do a bunch of examples with this, but this is essentially the kind of diagram that's going to be set up anytime you're dealing with an object that's on a ramp, or any sort of incline. All right, so let's get into some of these practice problems, right, using that formula, and then also kind of looking at what happens when we've got objects on an incline. So based on that other image we just saw, right, if we consider a weightlifter bench pressing a barbell that weighs 6.50 times 10 squared newtons through a height of 0.550 meters, there are two distinct motions, right? When the barbell is lifted up, and then when the barbell is lifted back down. Consider the work done on the barbell during each of the two motions. All right, so this one's pretty straightforward, okay? So if we look here, we think of the first one, right? We've got our barbell, and it's being pushed up, okay? We've been given that it's being pushed up through a displacement of 0.550 meters, where the force, right, the weight of the barbell, which is essentially the force of gravity, right, which is what you would need to overcome it, right, to get it to push up, is 6.50 times 10 squared newtons, okay? So similar to what we were just discussing, right, we're doing work to push this up, and we can use that formula. Work is equal to the force times the displacement times the cosine, and since it was going straight up, we'd use cosine of 0 degrees, okay? And this would give us a value of 6.50 times 10 squared newtons times the 0.550 meters multiplied by 1, okay? So the work done to push the barbell up is 357.5, but using 3 sig figs, it would be 358 newtons. And again, it would be in a positive direction because you're pushing it up, right? The work is being done up. Now, in the second scenario, where the barbell is being then lifted down, okay, you can kind of think of this in two ways. One, you can just do it the exact same way here and say, okay, work is equal to force times the displacement, and we saw from the slide that if something's coming straight down, we use a cosine of 180 degrees, right? You can think of it just as straightforward like that, where it's that force, the same one, of 6.50 times 10 squared times the 0.550 meters, and then cos of 180 is negative 1, which gives you the exact same value here, but just negative. right? Some people might even choose to think of it as well, I don't really need that cosine of 180. I can just kind of say, well, the work would be the same, but just in the opposite direction, right? And that would work as well. Another thing would be saying, well, if this was the original spot, right, and I moved it up, and now here I'm moving it down, you could instead think of the displacement being negative and not having to worry about the -1 there either. Okay, so again, this is a fairly straightforward example, but serves the purpose of just kind of introducing this aspect. Okay, moving on. So there's your solutions, same idea, right? Oh, and for some reason, I put work as newtons when it should be joules. That is a mistake on my part, right? So I just fixed that there, so your board should actually look like this, 358 joules, and then 358 joules in the negative, right? So still thinking force, so it shouldn't have been newtons, it should have been joules. Okay, my apologies. All right, so let's move on to a second problem, okay? So in this one, right, this is where we're going to add in that angled force, okay? So what we have done here is Jacob is pulling his wagon with 221.5 newtons of force at an angle of 39 degrees with the horizontal. If he achieves 2,142 joules of work while pulling his little red wagon, how much distance did he cover? Okay, so again, we've been given information here. All right, so we want to start by listing the information that we know. So what we know from this first one is that the work done by Jacob in pulling his red wagon was 2,142 joules. We know that the force applied, right, when pulling was 221.5 newtons, right? And if we go back just quickly to the question again, right, and it was being pulled at an angle of 39 degrees with the horizontal, okay? So we know that the angle being used is 39 degrees. So if we wanted to kind of get a visual of what was happening here, right, it's kind of like along the ground, here's the wagon that's being pulled, right? And it's not being pulled straight, okay? It's not being pulled just straight this way. It's being pulled like this, right? Which again, that makes sense, right? We rarely like stand level with something and pull it flat like that. We usually have it up at an angle and we're pulling along the way, okay? So this is what's happening. The force being applied is happening in this direction. So that's the 221.5 newtons. And this is the angle here of 39 degrees. Okay, we are wondering, okay, well, how much did this move? What is the displacement that's happening in this scenario? Okay, so again, remember that our formula was work was equal to force parallel multiplied by the displacement. Okay, so we have work, right? So work is equal to that force parallel multiplied by the displacement. We have the work. This force is not parallel to the object's motion. We need to figure out what is this force, right? What is that force parallel? So if you think about it, what we've done here is we've created a right triangle where we have the angle. This 221.5 newtons is the hypotenuse side, and this is the adjacent side length, right? So what we would be solving for here is the adjacent side length. So you'd be able to set up cos of 39 is equal to the adjacent, which is the force parallel, divided by the hypotenuse of 221.5 newtons. So to solve for force parallel, you just multiply both sides by the 221.5 newtons, and you get that cos of 39 degrees multiplied by 221.5, and that equals your force parallel. So notice how here, that force parallel is the same as the applied force multiplied by the cosine of the angle, right? So it's like that applied force multiplied by cos theta multiplied by the displacement. And once again, we're seeing that new formula that I introduced. It's just written in a different order, right? So it's still that applied force multiplied by the displacement multiplied by the cosine of the angle because it's not being done perfectly horizontal. But this is the trig that shows where that's going to come from, okay? So now ultimately what we're solving for in this case is displacement. So what we would do here is we would take the work, we would divide it by the applied force multiplied by the cos of the angle, and that would give us our displacement. So our work was 2,142 joules. I'm just going to do that over here, right? So that's 2,142 joules being divided by the force applied, which was 221.5 newtons, multiplied by the cosine of 39 degrees, right? And we do that, we would get a value of our displacement. So doing that multiplication and division, and we get 12.44 meters. Right, and again, we were able to have 4 sig figs, so we keep 4 here as well. All right, so that's how we can apply that idea of like a force parallel, right, with work done to be able to solve for missing values like displacement. Okay, so again, there's the solution, and we come to practice problem number 3. All right, so this is one of the ones that's a little bit different. As I mentioned, we need to look more at normal force and force of friction, because the object is not actually moving in a horizontal fashion. The object's moving actually on an incline. So we need to kind of bring in some of our knowledge of Newton's second laws and all of the forces that can act on an object, and then bring in the trig that goes with it. Okay, so here's the situation. We have a 100 kilogram box that rests on a 30-degree inclined plane. Due to friction, the box remains motionless. Find the normal force and the minimum frictional force. Okay, so let's start by framing the problem. Right, let's get an idea of what we're dealing with. Okay, so we have a box that's on an inclined plane. So we have a ramp, essentially. Okay, the ramp has an angle of 30 degrees, and here's our box. Okay, that has a mass. We know that the mass of that box is 100 kilograms. Okay. Let's think about what forces are acting on this particular box, right? Well, the force of gravity just pulls on it straight down, okay? The normal force acts on the box perpendicular to its motion. So its motion would have been going this way, down the ramp, right? This would be considered our force parallel. Our normal force is perpendicular to that, so it makes a nice right angle. Right, and notice that that's not exactly straight up, right? It's on that angle that way. Okay, so if we continued with this line, like that, okay, this is the value that will help us find our actual value of the normal force. Okay, and then again, this line being parallel this way, right? These two are parallel lines, so they have equal values, so this is also considered our force applied, okay? Or force parallel. This is our right angle. This 30-degree angle corresponds to a 30-degree angle up here, okay? And then we also have this force of friction that's working exactly against the ramp this way, okay? So these are all the forces that are acting on that mass, right? Our job right now is to find the normal force, okay? So our normal force is the sum of all of the vertical forces acting on this particular mass. And right now, looking at the vertical forces, really all we have happening here is this, right? And then this, okay? And this specifically acting in a upwards motion, okay? So what we would look at here is finding this value, which is going to be the same as this value here, right? It's at an angle, so it's here. So this is what we're looking for. So to find our normal force, right, we actually can use this triangle here with this angle. FG can be found, right? All we need to get force of gravity is the mass, and then assuming that we're on Earth, right? So FG is our mass times our acceleration due to gravity. Our mass of our object is 100 kilograms, and our acceleration due to gravity is our 9.81 meters per second squared. So we can get that value and say, all right, well, our force of gravity is 981 newtons acting in a downwards direction. Okay, now our normal force is, according to this 30-degree angle, the adjacent side of that right triangle. Okay, so that means that our normal force here would be found by taking the cosine of 30 degrees and multiplying it by the hypotenuse, which is the force of gravity. Okay, so doing that, we take cos of 30 degrees and we multiply it by 981 newtons. So our normal force in this case now would be 850 newtons. Okay, so there's our normal force. Right, that was the answer to part A, just finding the normal force. Now, part B has asked us to find what's the minimal force of friction. So what we've been told is that this box is motionless, meaning it's not moving, right? So that means that the force of friction is at least as strong as this force parallel, so that they cancel each other out and nothing's happening, right? If the force of friction is stronger than that, well then again, it's still not going to move down. Or if this force parallel was greater than that force of friction, it would be moving in this direction, right? Thinking about that idea of like winners and losers in terms of forces, right? If these are equal, nothing's happening. So in order to find that minimal frictional force, we need to figure out, well, what is this force parallel that I'm working against, okay? So remember, if we take a look at that, well, what is this value, right? So my force parallel is going to equal this value here, right? Because these lines are parallel, so these would have similar values, exact same values. So this, in regards to the 30-degree angle, is an opposite side length. So this would be sine of 30 degrees multiplied by our force of gravity. Okay, so that's sine of 30 degrees multiplied by our force of gravity of 981 newtons. Okay, so when we do that, we get a value of 491 newtons. Okay, so our force parallel here is 491 newtons, which means our minimal frictional force, right, has to be greater than or equal to that 491 newtons acting in the negative direction, so that this is either the same and we don't have anything moving, or it's greater, right? I mean, it's a ramp. It's not going to be moving up the ramp, right? Gravity's a little bit stronger than that, right? But it is just going to stay there and it wouldn't move. So this would be the least amount of force, right? Because we don't have the coefficient of friction in this case. We can't just calculate what it would be. Yes, we have the normal force, but we can't calculate the coefficient of friction. If we knew that this force of friction was in fact 491, we could use the normal force and the force of friction to calculate it, but we don't know that's exactly what it is. We just know that this is the minimal frictional force. Okay? All right, moving on. So let's take a look. So same idea, here you go. Practice problem number 4. All right, so this one, similar problem, right, where you have a girl on a sled is sliding down a snow-covered hillside. The girl and her sled together have a mass of 37.3 kilograms, and the slope is at an angle of 25 degrees to the horizontal. Find the girl's acceleration if the coefficient of friction is 0.122. Okay, so once again, we're going to start by framing the problem, trying to draw what's happening, state what we know, and then go from there. Okay, so we have similar diagram happening here, right? Girl is going down a hill. The angle that the hill makes with the horizontal was 22 degrees. Oh, sorry, 25 degrees. Just going to double check that. Yeah, 25 degrees. Okay, so we have the girl and her sled. I'm just going to use that with the box right now. Okay, we are told that the mass of the girl and her sled is 37.3 kilograms, right, combined. We've been told that the coefficient of friction is 0.122. I think 0. Okay. And again, we're looking at what's the acceleration that this girl is experiencing. Okay. So we know that we're actually moving down the hill. So we are, in fact, going this way. So this is our force that would be parallel to our motion. Okay. Force of friction would be pulling exactly opposite that. And notice I've drawn this arrow smaller because I know that this force has to overdo this force because we are, in fact, moving down the hill. Okay. Force of gravity pulls straight down. Okay. Normal force is perpendicular to the object. Right, so that would look like this. And in trying to calculate those things, we can create this right-angled triangle, right? Where this 25 degrees is equal to this here, okay? This value along the bottom, right, would be parallel with this line, so it would be the same. So this would be your force parallel of motion, and then this would be your normal force here, right? The same value, okay? Happening in that sense. So we are looking for the acceleration. So again, thinking about what we did with Newton's second law, we know that the sum of the forces, right, net forces acting on the object is equal to the mass times the acceleration, okay? Well, in this case, what we've got is, in terms of the motion of this object, the force parallel helps it move in a positive direction. The force of friction pulls back in the negative direction. So it would be force parallel minus force of friction is equal to mass times acceleration. And to solve for acceleration, we just need to find the difference here and then divide by the mass. So our force parallel minus our force of friction divided by the mass would equal our acceleration. All right, thing is, we don't have a value for the force parallel right now. Force of friction means we need to take the coefficient of friction and multiply it by the normal force. Coefficient of friction we have, normal force we currently don't. The only force we can actually calculate here is force of gravity, okay? But force of gravity will help us get normal force and force parallel, both of the things we need. So force of gravity is our mass times gravity. Mass is 37.3 kilograms. So Fg is going to be 37.3 kilograms multiplied by our acceleration due to gravity, 9.81 meters per second squared. So our force of gravity here will be 365.9 newtons acting in a negative direction, okay? Our normal force, right, is the adjacent side length here. So that would be cos of 25 degrees multiplied by our force of gravity. So Fn is going to equal cos of 25 degrees multiplied by Fg, which is the 365.9 newtons. So our normal force has a value of 331.6 newtons, right, acting in this direction here, okay, perpendicular to where the object is resting, right? Then we can calculate force of friction, right? So force of friction is going to be your coefficient of friction multiplied by your normal force. So Ff is mu times Fn, which is that 0.122, multiplied by your 331.6 newtons. Okay, and that gives us a value of 40.455 newtons. And again, acting in the negative direction because it's acting against the force parallel to the motion. Okay, so now we have this value of force of friction at that 40.455, right, acting in the negative. Okay, so what we need now is that force parallel. So our force parallel is here, which is the opposite side length of that triangle. So I would need to use sine, right? So the force parallel is going to equal the sine of 25 degrees multiplied by the force of gravity. So I'm just going to change these values here, right? So that my force parallel is equal to instead the sine of 25 degrees multiplied by that force of gravity of 365.9 newtons. Doing that, I get a value of 154.64 newtons. And then that would be acting in a positive direction because that's our direction of motion. Okay, so now I have my force parallel, can plug it in there. I have my force of friction, can plug it in there. I have my mass, can divide, and I'll get my acceleration. All right, so I'm just going to erase this so I can have the space again. Right, so my acceleration is going to come from my force parallel, which I calculated at 154.64 newtons. I'm subtracting my force of friction, right, so it acts in the opposite direction, so I'm going to subtract 40.455 0.455 newtons, and I'm going to divide that by the mass of 37.3 kilograms, and that's going to equal the acceleration of the girl in her sled. All right, so when I do that, I end up getting a value of 3.06 meters per second squared. Okay. So this concept of force at an angle is used not just in terms of work formula, right, that allows us to find the force that's parallel to the motion so that we can find the work done on the object, but it's also helpful just kind of going back to that Newton's second law, looking at all the forces acting on a particular object, right, which ones are helping the overall cause that we're trying to have happen, which ones are hindering it, right, which ones count as positive, which ones count as negative, and now just using some basic trig ratios to figure out kind of what's happening when this force is not just on a flat surface, what happens when it's on an incline. All right, so we're going to look at one final example together. All right, so again, there's your practice problem number 4, and here's 5. Okay, so this one, a little bit different, okay? So this one, the object is not moving on an angle, but the force is being applied at an angle. So it is kind of similar to the example where they were pulling their red wagon, right? And that one dealt with work. This one's going to ask us something a little bit different, right? But similar setup. So in this case, we have a 23.5 kilogram crate. It's dragged across the level floor. So the motion is directly horizontal, okay? But the force that's being applied is being applied here at an angle, right? And that force is 1.25 times 10 squared newtons, or just 125 newtons if you'd prefer. And the force is applied at an angle of 37 degrees with the horizontal. So this would be 37 degrees here, right, based on the center of mass. If the coefficient of kinetic friction is 0.290, what is the acceleration of the box? All right, so again, we start up, we frame the problem, we try and draw that free body diagram, we list what we know, and we go from there, okay? So again, here is our object, right, our mass. We know that the mass is moving in a perfectly horizontal direction, so this would be considered our force parallel to the motion. We know that the applied force has been applied at an angle, right? This is our applied force, and the angle that's been applied at is a 37-degree angle. We know that the applied force is a value of 1.25 times 10 squared newtons. We also know that the mass of the crate is 23.5 kilograms. Okay, and ultimately, we also know the coefficient of friction, which is 0.290, and we are looking for the acceleration of the crate. Okay, so let's think about other forces that are acting on this. So the applied force is here, right, which causes an overall motion of a parallel force to the right. Now, working against that parallel force is a force of friction pulling to the left, right? And we also have that force of gravity pulling straight down, okay? And then that concept of your normal force coming straight up, okay? Now, keep in mind though, normal force is going to be a little bit different here, right? Because of the fact that this is being pulled up at an angle, and we'll get to that in a second, okay? So one of the first things we can always do is say, well, you know, if I'm stuck at this point, I'm at least going to figure out what's f of g. If I've got the mass and I know that I'm on Earth, which we can almost always assume, I can at least start with finding fg, all right? So that force of gravity is going to equal your mass times your 9.81. So fg in this case is our mass of 23.5 kilograms multiplied by our 9.81 meters per second squared. So our force of gravity is here at a value of 230.5 newtons acting in the negative direction. Okay? Now, that would mean that our force parallel here, okay, let's look at trying to figure out that one. Okay, now our force parallel is parallel to the object of the motion, and we have an applied force that's up here. Okay, so think about this right angle triangle. Okay, we know the value of this hypotenuse. It's that 125 newtons. That means our force parallel is the adjacent side length here, so we could use cosine. So our force parallel is equal to the cosine of 37 degrees multiplied by our applied force. So that would be the cosine of 37 degrees multiplied by the 125 newtons. Okay, so that gives us an applied force of 99.83 newtons. Right, acting in that positive direction there. Okay, the next thing would be to find the force of friction. Okay, and we know force of friction is equal to mu times the normal force, which means we would need normal force. And the common thing to want to say to do in this case is go, oh, well, the normal force is just equal but opposite to your force of gravity, right? But there's something else that's happening here. Think about all of the forces acting in the y direction. You've got force of gravity pulling down, right? A normal force pulling up, but you also have this applied force that's been pulled up on the object as well. But we know that this object, this crate, is not actually moving up or down. So we know that all of the forces acting in the y direction, okay, so our F net in the y, okay, so our F net in the y-axis, we know is going to equal 0, because overall there's no motion going up or down. And all of the forces acting in the y direction are a sum of all those ones. So what we have in that case is we've got, right, so our F net acting in the y is you have your force of gravity, your normal force acting up, your force applied but perpendicular to the motion, here, also acting up, and then you've got your force of gravity pulling down. Okay, so again, we know that the sum of those three forces needs to be 0. So 0 is equal to that normal force plus the force perpendicular, and again, this is part of that right triangle where it's the opposite side length of the diagonal, and you know the hypotenuse, so we can use the sine of 37 degrees multiplied by your applied force of 125 newtons, and then you're subtracting the force of gravity that we previously calculated at 230.5 newtons. Okay, and then that allows us to actually solve for our normal force. Right, so I can figure this out and get a value. So 0 is going to equal to Fn plus, I combined the two, so I'll redo this. So sine of 37 times 125, right, so this perpendicular force motion is 75.23 newtons minus the 230.5 newtons. So I can take the 75.23 minus 230.5. So I get that 0 is equal to the normal force minus 155.27 newtons. Getting Fn by itself, I can add the 155.27 to both sides, and we just get that Fn is equal to 155.27 newtons. All right, so now that I have Fn, I can solve for my force of friction. Because my force of friction, I'm going to need to erase something again here now. Okay, so going back to this, okay, so my force of friction is equal to mu times my normal force. My coefficient of friction of mu is 0.290. My normal force I just calculated at 155.27 newtons. So my force of friction gives me a value of 45.03 newtons acting against the motion, so being considered negative, right? And again, ultimately, I'm trying to find my acceleration of the object. And so now I know that overall there's no motion up or down, so the acceleration is just to the right. So again, my F net is equal to mass times acceleration. I've got my parallel force pulling in a positive direction. I've got my force of friction acting against it, so I can subtract it, and that's mass times acceleration. So again, to get acceleration, I would just take this difference and then divide it by the mass. So my force parallel minus my force of friction divided by my mass will equal my acceleration. So my force parallel was here at 99.83. Let's see if I can do this up here, right? So my force parallel was 99.83 newtons. My force of friction was calculated at 45.03 newtons. And I'm going to divide that by the mass, which I just erased, and it was 23.5 kilograms. Right, so this is this up here, and that gives me a value when I subtract and then divide of 2.33 meters per second squared. Right, and then that's to the right. Okay. So a little bit of an extra thing added in there when it comes to finding that normal force. Okay, so if you're pulling at something and the force applied is at an angle, you need to kind of consider what's happening to your normal force, because your normal force is going to come from that calculation where the sum of all of the forces in the vertical is 0 because the object is not moving up or down, right? And then think about what are all the forces acting in the vertical direction, right? You've got your force of gravity pulling straight down. You have that applied force, but applied just in the vertical, so like the perpendicular applied force, right, which can be calculated using that right angle triangle, and then your normal force, all adding up to give you 0. And then when you rearrange that, you can solve for your normal force as we just did in this question. Okay, so that's it for this lesson, right? So you are going to get some worksheets, some involving the work formula and having to multiply by the cos of the angle in order to solve for the work done, or rearrange it to solve for displacement or force, what have you. And then you're going to have some questions that may not ask you anything about work, but will ask you to work on, okay, well, what's happening with the force at an angle, right? And solve for the acceleration of the object, or solve for the force of friction, anything like what we've seen, okay? And then that's your force at an angle lesson. You've got 2 worksheets to work at, and that's it.